Hi, I'm David Patel, currently a master's student at McGill University under the supervision of Professor David Patel. In this presentation, I will briefly describe the design that was submitted to IMEC for the SiEPIC passage run. But before I do that, I just wanted to quickly talk about silicon photonics in general. Silicon photonics allows for photonic devices at the nano and micro scales to be developed with a CMOS-like process. This allows the devices to be integrated or interfaced with electronics, leading to a broad range of applications, one of which is interconnects that could be at the intra-chip level, or for short-range communications. The design that I decided to implement is a demodulator that could be part of an integrated receiver for such applications. SiEPIC gave me the training and the resources to create these devices and have something that could be characterized. It also offered a hands-on learning for silicon photonics. This was particularly useful as I was able to not only study the subject from papers and textbooks, but actually simulate them and create layouts. My passive design consisted of 2x2 and 4x4 multimode interference couplers. The 2x2 MMI are essentially the same as 3 dB couplers, and input signal is split in half with a pi phase difference. The advantage is that the MMI offers a higher fabrication tolerance, they work over a larger bandwidth, and is also less susceptible to polarization differences. However, this comes with the disadvantage that they are larger than the other devices which offer the same function. The 4x4 MMI was used as a traditional 90-degree optical hybrid. So essentially, one of the inputs is phase shifted by an additional 90 degrees at each output. The MMI couplers can then be used with a delay line of 1 baud to create a QPSK demodulator. In the design process, several simulations were performed to optimize the MMI with respect to loss and to obtain equal power splitting at the outputs. In addition, a shallow edge was also used to reduce the index contrast in one dimension. This would reduce the phase errors. Tapered inputs were also used to reduce loss by exciting only the lower order modes in the multi-mode section of the MMI. Finally, the testing of the devices is planned to be performed with a fiber array. In this design, both the inputs and outputs are on one side of the device. First, each individual MMI will be tested to measure the phase difference at the outputs. Then, an OSA will be used to determine the free spectral range of the Mach-Zehnder delay interferometer. If the FSR and phase differences agree within a certain range, a demodulation test will be performed with the PPG and an error detector. This concludes the short presentation of my passive design. Thank you.